The structures we've looked at so far all had bonds and no lone pairs on the central atom. But there are molecules that have one or more lone pairs on the central atom. In this case, we find that we can describe the geometry in two different ways. We can describe the geometry of the electron groups, how they are arranged, and we can also look at the overall molecular geometry, which describes where the atoms are. You have to identify the electron geometry first, and that helps you to understand what the molecular geometry is. When there are no lone pairs, these are the same. The electron geometry and the molecular geometries are the same. So let's look at ammonia. Here's the Lewis structure for ammonia. So there are 3 bonds and a lone pair on the central atom. That's 4 electron groups. And 4 groups arrange themselves like 4 balloons and make a tetrahedron. So here we have an illustration of that. We have the 3 bonds to the hydrogens. Those are 3 of the groups. And then we have a lone pair. So here's the lone pair kind of sticking up. So the geometry of the electrons is tetrahedral. When we go to see the molecular geometry, we imagine that that lone pair is invisible. And we're just going to look at the atoms. So if that lone pair is invisible, I can make it invisible. It goes away. We're just looking at what's left. And what's left is something that's triangular, but it's not flat, right? Because the lone pair was pushing these guys down. And so the angles here are not 120, they're roughly 109.5, like a tetrahedron. So the name of this molecular geometry is trigonal pyramid. So it's trigonal, but it's a pyramid. It's a very shallow pyramid, but it's a pyramid. It's not trigonal planar. Any questions? So my approach is you look at the electron groups, you imagine what the balloons would do. You build this balloon structure in your head. Most people, after watching me do the balloons, you can kind of visualize what would happen. Any lone pairs, you imagine those as invisible balloons, and the molecular geometry is describing what's left. We're not going to pop the balloons, because if we popped the balloons, then we'd have fewer groups and the shape would change. That lone pair is actually more repulsive than a bonding pair. Well, I guess I don't need to go over there. We can use this one. So that lone pair sticking up, here we've drawn this sort of like a balloon and made it quite large. This lone pair, even though it's just 2 little electrons there, is more repulsive to these other bonding pairs than they are to each other. And so they're like, ooh, he's got like body odor or something, and so I don't like the rest of you, but I'm willing to get a little closer to you to get away from him. So what we observe is that the angle here is 107 degrees in ammonia, not 109.5 as we would expect. This illustration over here helps us to understand why that is. When the 2 electrons in a bonding pair are shared between 2 nuclei, it sort of constricts them and they get squeezed into this sort of a shape. If you have a lone pair attached to a nucleus, it can spread out, and so this is going to take up more space than that is. And so it's going to push the other things a little closer together. So when we have lone pairs, it affects the bond angles.
So together with memorizing like the angles of shapes without lone pairs, you also have to remember the lone pair shapes.
That's a good question. So essentially you're asking, do I need to remember that nitrogen has a bond angle of 107? No. What I want you to remember is that nitrogen has a bond angle that's less than 109.5. Because they're going to vary, right? And so what I want you to know is the bond angles for linear, trigonal planar, tetrahedral, and then trigonal bipyramid and octahedral. If you have a lone pair, the bond angles between the other electron groups will be less than what we expect, and that's good enough. Any questions? Other questions? So let's look at water. Lewis structure for water, we've drawn that. We typically draw it like this, and you might predict that that would be a linear molecule. But when we look at the Lewis structure, we see that there are 4 electron groups. 4 electron groups make a tetrahedron, right? So the electron geometry is a tetrahedron. We would predict 109.5 degree angles. To find the molecular geometry, we imagine that these lone pairs are invisible. I can make them invisible. This is what's left. That has the very fancy name, bent. It's a bent structure. You know, trigonal bipyramid is all fancy and bent. Yeah. Sometimes it's called angular, but our book calls it bent, and I prefer that. So the molecular geometry is bent. We should know that the perfect bond angles in the ideal tetrahedral angles are 109.5. When we look at these 2 lone pairs, we say, okay, those are going to be, they're going to take up more space. They're going to push the bonding pairs a little closer together. And so I expect you to be able to tell me that this bond angle is less than 109.5. It's actually 104.5. But all you need to know is that it's smaller. We should understand the relative repulsion of these different electron groups. 2 lone pairs are going to repel each other the most, which makes sense because they take up the most space. A lone pair and a bonding pair is sort of intermediate in repulsion, and 2 bonding groups are going to have the least amount of repulsion towards each other. So the number of lone pairs affects the bond angles. With methane, we have no lone pairs. We have an electron geometry. All of these have an electron geometry that's tetrahedral. This one has no lone pairs, 1 lone pair, and 2 lone pairs. So here we have the expected angle of 109.5. In ammonia, it's smaller, it's 107. It's smaller still in water, 104.5, because there are 2 lone pairs out here, and those 2 lone pairs are going to repel each other a lot. Yes?
So will those numbers be consistent pretty much throughout?
No. Those numbers would not be consistent throughout all different, because you can have other molecules that have this shape, 2 lone pairs and two bonding pairs. The angles would not be necessarily the same.
Would it be around that area?
Well, they would be a little bit less than the perfect tetrahedron. And that's good enough, right? It's important that it's a little smaller, but how much smaller at this point is not. Yeah. It depends on the size of the atoms and all kinds of other things, and we can just skip that. Good question. So let's look at sulfur tetrafluoride. Draw the Lewis structure, it says, so we'll do that. So sulfur and 4 fluorines. And then we have to think about how many lone pairs, not lone pairs, how many electrons. Sulfur has 6, and we have 4 fluorines, and they each have 7. So So 4 times 7 is 28, and 6 is 34. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need one more. Can I put that on the sulfur? Straighten that one out, it's messy. The sulfur in period 3? It is. Period 3, 4, 5, 6, those can expand their octets. So I can put that lone pair on the sulfur on the central atom. The fluorines can't handle more than an octet, so I cannot put the electrons on them. I can only put them on sulfur. So when we look at sulfur, how many electron groups does it have? 5. 5 groups make what shape? Trigonal bipyramid. So there's a triangle here, and it makes a pyramid on the top and a pyramid on the bottom. In the trigonal bipyramid shape, all the bond angles were not the same, and so all the positions are not the same. So we have a choice between putting this lone pair in an axial position or an equatorial position. This lone pair is going to take up more space, and so we need to put it in the position where it has more space. If we put it up here in the axial position, it's going to have 90-degree bond angles with 3 atoms. It's going to push them away a little bit, but that's what it starts with. If we put it here in the axial position, it's going to have 90-degree bond angles with 2 atoms, but then 120-degree angles with the others along the equator. And so it's got a little more space here, and so that's where it's going to go. If we made a balloon structure and made this balloon extra big, that's where it would want to be. It would want to be along the equator. Yes?
In the first picture, I'm having a hard time visualizing like the axial versus the equatorial from that.
Okay. So here's this little girl. Oh, well, maybe that's a little too high. Here's her head. No, that wasn't too high. Never mind. Here's her head, and here's her legs. Maybe she's doing some sort of a twirly thing. And so this is her skirt. Her tutu sticking out. Does that help? So equatorial is the tutu. And axial is head and feet, above and below. The difference between the 5 and the 6 groups, bipyramid and the octahedron, is how full the skirt is. So here, the skirt has 3 groups. In the octahedral shape, it's got 4 groups. But because there's only 3 groups around here, these bond angles are 120. And so in the equatorial position, there's a little more room than in the axial position. And so the lone pair goes where there's more room. It always goes to an equatorial position. So
So like in the first one, X, what do you call it, the blue one?
This is the blue one. This is a lone pair.
Okay, so the lone pair is too close to...
Here the lone pair is too close to these other atoms. It's 90 degrees away from 3 atoms.
But in the middle it's 120?
Yeah, here it's got 90-degree angles still. You can't avoid that, but it's only with 2 atoms, and then these guys are further away, and so it's got a little more breathing room.
So that's what you wanted to have more space.
Yeah, because this is more repulsive,
Yeah.
and so it needs more space
It's more repulsive because it's a lone pair?
because it's a lone pair.
Okay.
So if we go back and look at this, so this is a bonding pair, and this is a lone pair. The bonding pair gets pulled in at both ends, and so it's got more of this sort of a football shape. The lone pair is pulled in at the nucleus, but the other end is big and fat. And so when you put things like this and this together, this is going to take up more space.
Yeah. All right, yeah,
Does that make sense? Once you ask enough questions that it starts to make sense, this model is actually quite simple, and it's easy to visualize. And you can even, buy some balloons on your way home and some string, get good strong string. I don't know what's wrong with that yarn. But you can tie them together and see what happens. So for this molecule, our electron geometry is going to be trigonal bipyramid because it's got 5 groups. But then we need another name for the molecular geometry, because for the molecular geometry, we're not looking at that lone pair. It's there, it's big, and it's repulsive. It's taking up a lot of space, but it's 2 teeny tiny electrons. There's no atom there. So the name of this is seesaw. So if you actually make this model and you can tip it on its side and you see it acts like a seesaw. So that's what it's called. Again, another fancy name. There's bent and seesaw, and then there's those others that are so fancy. Well, what if we had 5 electron groups and 2 lone pairs? So this happens with bromine trifluoride. When you look at this formula, bromine and 3 fluorines, you might think, well, that's going to be trigonal planar. It's got 3 atoms around it. Why is it going to be anything else? But the lone pairs. You have to look at the Lewis structure. Here, bromine has an expanded octet, and so it's got 2 lone pairs and 3 bonding pairs. So again, 5 electron groups, trigonal bipyramid, but the lone pairs are going to occupy the spaces that have, the positions that have more space. So the equatorial positions. So now we're going to have 2 lone pairs in the equatorial position. The electron geometry is trigonal bipyramid. The molecular geometry is T-shaped. If we have 5 groups with 3 lone pairs, again, the next lone pair would go into the equatorial position, and now we have a little girl dancing in an invisible tutu. She's not naked, she's got a leotard on, but her tutu is invisible, the skirt part, right? They're going to take the equatorial positions because there's more space there. So when we don't look at the lone pairs, what we see is this, and that is a linear geometry. So the molecular geometry for this one is the same as something with 2 electron groups. But there are 3 lone pairs around the center. Any questions? Yeah.
Since there are 3 lone pairs, do the lone pairs have the same, they push each other away as much as they do to the other electron groups?
That's a good question, because we were talking about, like with ammonia, that the lone pair is going to push the bonding groups closer together. In this situation, because these are already, the effect of the lone pairs is that they can't really affect anything, because these are all symmetrical around, and so they're repelling, but if they push this one over that way, the other guys on the other side are going to push it back. So you still end up with a 180-degree angle, because their extra repulsion just cancels itself out, basically. Good question. Bromine pentafluoride has 6 electron groups, 5 bonds, and 1 lone pair. So that's this guy right here. You see there's 6 groups. So 6 groups makes an octahedral shape. And then one of those positions is a lone pair. In an octahedron, all the positions are equivalent. All the angles were 90 degrees. So we can talk about axial and equatorial positions, but they're really all the same. So you can stick that lone pair anywhere you want. It's not going to affect the molecular geometry. So you make that invisible, and we're left with this. And that is called a square pyramid, because we've got this square base, and it goes up to a point. It's a pyramid. Now, these angles, how are they going to be affected by that lone pair? They'd be squished a little bit. If we have two lone pairs with the 6 electron groups, so here, xenon tetrafluoride, there's our Lewis structure. We have 4 bonding groups and 2 lone pairs, total of 6 electron groups. Makes an octahedron. We've got 1 lone pair in here. Now the other lone pair will go on the opposite side, because 2 lone pairs to each other are the most repulsive. So if this lone pair can avoid it, it doesn't want to be near the other lone pair. So it'll go on the opposite side. So the lone pair angle is the biggest. So we make those invisible, and then what we have is a square planar. So this is a square and it's flat, unlike the tetrahedron that has 4 things, but it's not flat. So in my balloon structure here, what we've got is the pink balloons now are the lone pairs. So if those pink balloons were invisible, what's left would be a square that's flat, right? So here's a table from your book, which is helpful in that it summarizes all of this. But what I would encourage you to do is try to answer questions about electron and molecular geometry by thinking about balloons and what those would do. And then you can check and see if you're correct by looking at the table. But don't just rely on the table, because I am not going to give you this for an exam. Just not. So summarizing VSEPR theory. The geometry is determined by the number of electron groups in the central atom. We figure out how many electron groups there are by looking at the Lewis structure. An electron group is any one of the following: a lone pair, a single bond, a double bond, a triple bond, or a single electron, as in a free radical. So a triple bond is 6 electrons, but it's 1 electron group. Because those 6 electrons are stuck between the same 2 atoms, they cannot get away from each other. The geometry of the electron groups is determined by their repulsions to each other. The bond angles can vary because multiple bonds are bulkier than single bonds, and lone pairs are the most repulsive.